Hello, let's look at some problems from Module 8, exponential and log functions. So let's look at the first problem. So before we start the first problem, let me just remind you, try this problem on your own first before you watch me going over it. Okay. Especially number 1. So it says colony of bacteria is being grown in a laboratory. Colony contains 1 million bacteria at noon, which means time 0, the initial time. And population is doubling every hour. Okay. So now part A is just guessing. How long do you think it would take for population to exceed 1 billion? So that's 1,000 million. Okay. So here's 1 million and it will be 1,000 times larger. How long it would take? So 1 billion, 2 billion. Write down your guesses. So I'm not going to write anything here. Just write down your guesses. Your guess might be wrong, but that's not the point here. The point is to engage our mind to think about this exponential relationship, how it works in terms of increasing or decreasing. Okay. So doubling every hour. So you can write maybe after 10 hours, 20 hours, or 100 hours, whatever you think. Okay. So write down your guess. So would it be like 10 hour or 20 hours or 30 hours, or it could be even like 100 hours. Right? Okay, so write down your guesses. And as we explore in part B, okay, in this problem, see if your guesses are way off or somewhat close. Okay, but that's okay if it's way off because, again, the exponential function is not as intuitive in terms of a two quantities relationship. Okay, so make a table showing how this population bacteria changes as function of time, 1 hour from the noon, 2 hour from the noon. So one means 1 hour from the noon, 2 hour from the noon. So like 1 p.m., 2 p.m. That's another way to think about it. Okay. So for now, we're going to leave the third column blank, which means this column. So we're going to do this column first, this column right here first. So at the 0 hour, we start at 1 million. After 1 hour, it doubles, so 2 million, right? Then after that, it'll be 4 million, which just doubles, right, from the previous population. 8, 16, 32, 64. Okay. So let's try to write an exponent in third column. Okay, so to recognize a pattern of relationship. Okay. So first one, since it doubles, we can think as 1 million times 2 to the 0 power. Again, anything to 0 power is 1. Okay. And maybe I will show that after problem 2 why anything to 0 power is 1. Okay. So this still gives us 1 million. So then we have 1 times 2 to the first power, which gives us 2 million. And we have 1 times 2 to the second power, 1 times 2 to the third power, 2 to the fourth, 2 to the fifth, 1 times 2 to the sixth. Okay. So let's plot this graph. So that means we're going to graph 0, 1, let's say somewhere here, and 1, 2, 2, 4, 3, 8. So 8 will be somewhere here. And 4, 16. 5, 32 was all the way here. And you can see that at 6 would be way high. So it grows exponentially. And as you can see, it's growing really fast. Right? Very growing rapidly. That's the one characteristics of exponential function when it's increasing. It also could be decreasing, but we're looking at increasing that example here. Okay. So just for exercise, just like I went over the main video, this tells us that we have a generic function of 1 times 2 to the t power. Like that. So this function shows relationship between time and the bacteria population growth right here. Okay. So, I meant to write it here, sorry. General expression. Okay. So let's just go back to the first question. How long will it take to take 10, essentially 1,000 million, which is 1 billion? So we can set this equation. So 1, we don't have to write it once because it doesn't change the quantity. But it's still good to have a good habit to put an initial population. Okay. So 2 to the t. So it's asking when will be a 1 billion, which is 1,000 million. So we're solving for this essentially, right? So there is not going to be a whole number in terms of what exponent t to the 2 to the y power will give us t. It's not going to be a whole number exponent. It's going to be some kind of decimal, right? Okay. So just for an example, 2 to the 10 power gives us 1,024. So it would take about, we can say about 10 hours, a little less than 10 hours, just for estimate, right? So if we go back to the first question, it would be actually about 10 hours or little less than 10 hours to reach 1 billion, right? Again, if it's not intuitive, that's okay. It's because that's how exponential growth works. It doubles every time, so it grows really fast, right? It's different from linear relationship where it's increasing the same amount every time, where we add or subtract in linear growth. But in exponential function, if we multiply by a factor, and that could make it grow really fast. Again, it also could make it decrease. Like when we let's say if it decreased by half every time, right? So about 10 hours, it would take about 10 hours to exceed 1 billion, which is 1,000 million. Okay. Less than you thought? Yeah. So to think about, right? So let's just quickly, I'm sure you've seen this before, right? Why is any positive number to the 0 equals 1? Okay. Why is that? Okay. So something you definitely have to know. Again, a is only a positive number. Okay. So it cannot be 0. Okay. So let's look at an example. If I do 2 to the negative 1 times 2 to the 1 power, this gives me 1 over 2 times 2, which is 1, right? But if I follow the exponent rule, since base is same, I have 2 negative 1 plus 1, which is 2 to the 0. That's why 2 to the 0, which is same as this, same as this, same as this, was 1. Okay. So this is why any we can think as a 0 equals a to the maybe some number. Let's say x minus x exponent. So then that can be written as x, a to the x times x to the negative x, which is same as a to the x times 1 over a to the x. A to the x, a to the x cancels out. We have 1. Okay. So this is why anything to the 0 power, but 0 to the 0 power is undefined. Okay, it does not exist. Well, this does not exist. It's undefined. Okay. So if you ever wonder why, okay, this is why. Okay. Now with negative number, we have to be a little careful. So let me just do it quick. For negative number, if I have, let's say, negative a to the 0 power, right, we have to differentiate between negative a to the 0 power and negative 8 of 0 power, right? They're not necessarily the same thing. So either we write it like this or we write it like this. Okay. So if we do this one, it will be, this one will be 1. So this will be actually negative 1. Whereas for this, it will be still just 1 because we have negative 8 times 1 over negative 8, which gives us 1. So it matters where parentheses are. Okay. So keep that in mind. That's why I didn't want to say this works for all negative number. If it's negative entire thing to 0 power, then it will be 1. But if we look at written like this, it will be exponent first, then multiply negative 1, right? So keep that in mind. Okay, so let's really try to understand just the conceptual meaning of exponential functions. Okay, so explain whether the below function represents exponential or not. Okay, so we don't need to come up with equation here. We just purely think about it in terms of relationship. So the way we look at it is as x quantity increase one at a time, what's happening to the y quantity, fx, the output quantity, is decreasing by here 30. So let's subtract 30. Here also decreased by 30. It also decreased by 30, right? So we're subtracting, or we can think as adding a negative number. So this is actually a linear relationship because we're adding or subtract same amount. Linear relationship also means the constant rate of change is the average rate of change. Okay, so this is not exponential, okay, because it's a linear. Okay, so not all functions are either linear or exponential. There'll be some other things that can be described in those two categories, but it happens to be linear for number 3, and so it's not exponential. How about number 4? Again, always pay attention to input quantity first. It's increasing the same amount. Change in x is same, one at a time. Uniform successive change, changing one at a time. What's happening to f of x? Okay, here, yeah, we can think as we add 20, right? But we don't add 20 here, right? Oh, sorry, we add 10 here. From 10 to 20, we add 10. But second times, we actually add 20. Now here we add 40. So this is actually, we're multiplying 2 at a time, right? Because we multiply 2 at a time, this is exponential. Okay? Exponential functions. And if we multiply 0.5, they'll be still exponential. Even if we multiply, let's say half, it will be still exponential function. Okay? So this is, again, the core meaning of exponential function. The output quantities is multiplied by a factor. As it will increase if we multiply by number greater than 1. If we multiply a number between 0 and 1, it will be decreasing, but still exponential relationship. Okay, so let's try to graph a exponential function right here. Okay. So pause the video, try on your own, then come back. So it says include at least 2 negative points. So let's do -2, -1, 0, 1, 2. Okay. So again, these are just points. These are not the only points, of course, because this function, right? Domain is everything. Domain is -infinity to +infinity, because we can plug any exponent. So when we plug -2, we get 2 to the -2 minus 1, which is 1 over 2 to the second minus 1, which is 1 over 4 minus 1 gives us -3 over 4. So when it's -2, let me mark it here. -2, if this is 1, -1. Okay. So -1, we have -3 over 4, which is a little bigger than -1. So let's say somewhere here. Whereas -1, we have 2 over -2 to the -1 power minus 1. 1 over 2 minus 1 gives us -half. So -half right here. And 0, 2 to the 0 gives us 1. So 0 is 1. But actually we have to subtract 1, right? Sorry. So I meant to write. -1 is 1 minus 1 equals 0. So when it's 0, we actually have 0 in this case. And 2 to the 1 minus 1 gives us 1 right here. And 2 to the second minus 1 gives us 4 minus 1 gives us 3. So 3 right here. So if I were to connect this is the graph. Plus some points, right? Now, this function, why does it have values below x-axis, right? It's because this function is actually transformed to down 1 from 2 to the x graph. So 2 to the x graph will actually look like this. Right, this green graph right here. This would be 2 to the x. And we went down 1 from 2 to the x. And this function, the green function, also has a horizontal asymptote y equals 0. But for red function, which is f of x, it will have horizontal asymptote at negative y equals -1. Y equals -1 would be a horizontal asymptote. Okay. So for this function, let's just for practice, domain is still -infinity to +infinity. But now range has changed. Range in basic function, basic parent function, the range is 0 to +infinity. But because of -1, we went down, it will be -infinity to positive. -1 to +infinity to be range for f of x. Okay. And you can also think, let me just write it bigger here, 2x, 2 to the x minus 1. This output can never equal -1 because we can make this value very small by putting negative exponent. If I put very small exponent, very small number there, it will make this entire quantity very small. Okay. But still, it will never be 0 because raised to any power, we cannot obtain 0. So that's why we'll be approaching -1 from the left side. Okay, now it comes to the log. Okay. Graph y equals log 2 of x. Again, there is generic characteristics that I went over in the main video. But I think the way I'm going to draw, it will make more sense in terms of procedure wise. Okay. Yeah, so there are some points if you want to memorize, that's fine. But if you do what I say here, there's less thing to memorize and you can actually make more conceptual connection to exponential function. So the first thing we have to remember is log is just, well, not just, but log is an inverse of exponential function. Okay. So here is this. So how do we find inverse function? Let's find inverse function of this. Remember in module 1, I believe, how do you find inverse function? First, switch in x and y. Like this, right? Oops, sorry. Then solve for y. How do we solve for y? We have to rewrite in exponential form. Okay, so let me actually go to right here. Rewrite. Again, so this is where we think about the meaning of log. Log means, this means 2 raised to what power, raised to what power, it will give me y. And the power here actually is x. So this is x. So we just solve for y. Y equals 2 to the x. So this function is inverse of this function right here. So why do we find inverse function? Because it is easier to find point using this. So let's find this points first. So here's x. And let's say 2 to the x. And yeah, let's again always plug at least 1 or 2 negative numbers. So it will be half, 1, 2, and 4, right? Now I'm going to draw another table. Now I'm going to draw, draw or make table for log base 2x. Now it's inverse, so we're going to use same points. Now we're going to switch its place because we flip domain and range in the inverse function. So when x is half, it will be -1. Looking at this, 1, 0, 2, 1, 4, 2. So now we're going to use this table right here. Oops. This table right here to draw a log function. So finding exponential function actually allows us to find points from exponential function, then we invert it. This is invert. We inverted it, right? So then we're going to plot these 4 points. Okay, so let's plot those. So half, let me mark it here. When it's half, let's say here, it's -1. So -1, -1. When it's 1, it's 0. When it's 2, it's 1. When it's 4, it is 2. So we'll go like this. Now, one thing we must remember about log function graph is that we have a vertical asymptote. Unless it is shifted, we have a generic vertical asymptote at y equals 0. So it will not cross or touch. Okay, the graph will go like this. Okay. And it's because the domain of log function, the domain of this, is always greater than 0. We cannot plug 0 in there for domain of log function. Okay, so there's something to keep in mind. So this right here is the graph of log base 2x. Okay, so this is one way to do it, where we draw x, we find the inverse function by switching x and y. Do this, find some points, 4 or 5 points. Again, make sure you include at least one negative numbers when you plot points, and then invert it, then plot these, and give us log function. But again, you must remember log function has vertical asymptotes, restrict domain. Okay, so let's do some practice of converting log to exponential. They're equivalent, right? So I'm going to do A, then pause the video and try B and C on your own. Then I'll go over it. Okay. So we want to convert this to logarithm. So log, what goes in here? Right here. Base. Base is x. Okay. And here will be the answer, 17 equals t. So that means x raised to t power will give me 17. Okay. So using the same idea, try B and C on your own. Pause the video, okay, and come back. Okay, so let's try again. So then we have log. Okay, here goes base. Base here is 0.05. Okay, and this is answer we get is y, and exponent is the output, -4. Again, we can have negative exponent. That's totally fine. But inside, this y value must be positive. How about this one? We have log base 10. And if I raise 10 to the s power, I get pi. And we need exponent s. And for log base 10, this is called common log. Sometimes we don't write just 10. So actually, that's the most times. So if you see log with no numbers in the base, it means 10s imply. So it's the same thing. Okay, similar idea. Now we're going reverse. So number 8, why don't you, again, pause the video and try on your own. Then I'll go over it. Okay. So every time we see log, we have to think ourselves in our mind, a raised to what power gives me 10? According to this expression, it would be -7. Okay. So when we just look at this, sometimes they don't give you equal. This will give you an output quantity. That is an exponent that needed for 10 to get, this will give an exponent needed for a to get 10. So look at here too. X raised to what power will give us y. That's what this expression is saying. So even if there's no equal sign, you still have to be able to translate this in your mind. And according to this, it says 13. Same thing. Now ln is same thing as log base e. E is the number, and we have to treat it like a number. B. So this is saying, oops, let me not write this. So what we have here is log e of b equals a. So this is saying e raised to what power will give me b? A. Right? So this is how we convert it. Okay, so let's look at number 9. So number 9, again, I'll do the part A to demonstrate and try to be on your own. So it says find the domain of the following log functions. So domain log functions that this input must be greater than 0. Okay. So that means the 3 minus x must be greater than 0. Okay. So that means x must be less than 3. Not less than, equal to, just less than 3. So in terms of in terms of interval notation, right? It will be negative infinity to 3, excluding 3. So this is the domain. So part B, why don't you try? Okay, pause the video. At least set up the equation, right? Okay, so same idea. Input has to be greater than 0. Well, let me use different color to avoid confusion. So then we know that x squared has to be greater than 8. when is x squared greater than 8, right? It will be greater if x is greater than square root of 8, or if x is less than square root of negative square root of 8. Okay. So if you think of number line, let me look at here, square root of 8. If I square the square root of 8, I get 8, right? And if I square a number bigger than, or any number here, if I square those numbers, I get number bigger than 8. Okay, so anything here is good. But then why negative square root of 8? Because if I square negative square root of 8, I get 8. But if I also square a number less than negative square root of 8, so let's say negative square 9, if I square this number, it also gives me 9. Because if you square a number, it's always positive. So 9 is greater than 8, so any number here is also fine. So for this problem, the interval is, let me write here, negative infinity to negative square root of 8, and square root of 8 to positive infinity is the interval for domain. So let's look at number 10. Number 10 says solve this equation. So here, base is same, right? 5 raised to this power equals 5 raised to this power. So since base is same, we can let exponents equal to each other. Again, we cannot do this unless base is same, right? If it's like 3 raised to this, 5 raised to this, we cannot do this, right? Because we both have same base in the both side, we can just let, oops, sorry, I made a mistake here. We can let exponents equal to each other. Then just solve. Subtract 3x both sides. X minus 5, x plus 2 equals 0. X is 5 and negative 2. So solution set is negative 2 and 5. So there's one extra step of just comparing the exponent. Okay, otherwise, this is just solving, right? Solving a regular equation. In this case, quadratic. Okay, so let's simplify. Okay, a to the 2/3 power. Okay, so what does that mean? So this is just kind of review of exponent. A to the 2/3 power. Way we can look at it is we have a 8, and we can think as 2 times 1/3 an exponent. Okay, so make sure you understand the basic property of exponents from algebra concepts, right? Because we need to be able to simplify this thing comfortably to work with exponents, since we're talking about exponential relationship, right? Okay. So let me actually, this is distracting me, sorry. Okay. So before we actually look at this problem, remember on the side note, x to the half power is same thing as square root of 2. Okay. Then x to the 1/3 power is cube root. I don't know what root 2 here, x. It's cube root of x. Okay. So here, the way we can think of this as is we have cube root of this thing, a to the 2nd power, which is cube root of 64. And cube root of 64 is 4. 4 times 4 times 4 gives us 64. Okay. Let's get 11b. Now there's also simplifying. So we have e to the 10x. We can rewrite this as e to the negative 30 power. Now we have the same base, right? Multiplying. That means we can just add, the exponents with one base. So we can write it as e 10x minus 30. So this is same expression as this right here. Okay. Okay, so let's look at 12. So solve, right? So in order to solve this, again, I'd like you to pause the video and try to rewrite this as exponential expression first. Okay, and once you've done that, you can come back and we'll solve for x. So according to this, it tells us that 2 raised to third power will give me 5x minus 10. And now we're just solving for x. It's just a linear equation now. There's one little catch, and I'll tell you in a second. So we solve for x, right? So I'm going to add 10 both sides. So this is 8. So I have 8 plus 10 equals 5x. So then we get 5x equals 18. X equals 18 over 5. Okay. So one thing we have to be careful here, because domain, we cannot have negative number or 0 inside of log. We have to see when I plug this number, when I plug this number right here, would it give me negative number inside of log? Right. If it does, that's not part of solution. So in this case, 5 times 18 over 5 gives us 18. 18 minus 10 gives us positive 8. So this is okay. So this is a solution. So it's something you want to be mindful that domain is restricted in log. Okay. And we'll do more practice of these, or well, not more. I mean, we'll look at more problems like these on module 9 as well. Okay. But it's important for us to mindset of domain is restricted for log function. So why don't you find domain of this one right here, 13a. Pause the video, try on your own, right? And come back. Okay, so domain again, we're strictly looking at inside. This must be greater than 0. So 2x greater than negative 1, x must be greater than negative half. So in internal notation is negative half to positive infinity. That's the domain. So what is, sorry, this is supposed to be, let me just change f here. Okay. This is all f. So what is f of 3? So plug 3 here, right? So f of 3 is log base 3, 2 times 3 plus 1 minus 2. So let's simplify. Log 3, this is 7 minus 2. Log 7, log base 3 is 7 minus 2. Right? Okay. So then, what do we do? So again, this is important for us to think about. This is asking what exponent, 3 raised to what power will give us 7. So 3 raised to what power will give us 7, right? And as you can tell, this exponent is not a whole number. Okay. So in that case, in reality, not only, but one of the way we can find this is using calculator. Okay. But again, you won't need calculator in this class. So for now, for this one, this is a number. This is number minus 2 is a number, right? So we have to see this as a number. This expression is a number. Sorry, my pen keep slipping. Okay. So what point is on the graph? So just for practice, again, the homework, when you do this in homework, it will give you, actually you'll be able to find this number, a whole number. For this problem, we can just write it as 3 comma log 3 7 minus 2 is the point. Okay. Okay. So I did this so that we can practice treating log 37 expression like this as a number. Okay. This is just complicated decimal number, but it's still a number, like pi or e, right? So f of x equals 1. What is x? So log 3 2x plus 1 minus 2 equals 1. What is x? Let's solve for x, right? So first, before we rewrite exponential function, we have to isolate this. So I'm going to add 2 both sides. So I have log 3 to x1 equals 3. Now we are ready to rewrite in exponential function form. So we have 3 to the third power gives us 2x plus 1. Now solve for x, right? Then 2x equals 3 to the third power is 27. So 27 minus 1. X equals 26 over 2, 13. So when x is 13, y is 1. That means we have a coordinate point of 13, 1. That's what I mean by what is the point on the graph. Okay. So what is the 0 of f? So just rewrite f, which is log 3 2x plus 1 equals 0. And so for x. Right? Again, I'd like you to pause the video and try on your own. What do you think we should do here? Right? How can we solve for x here? 2x plus 1. Right? So pause the video, try on your own, and come back. So the way we do it is, again, once we have a only log expression on one side, we can try to rewrite it as exponential form. So this tells us that 3 to the 0 power will give me 2x plus 1. So now solve for x. 3 to the 0 power is 1. So 1 equals 2x plus 1. Subtract 1 both sides, we get 0 equals 2x. So in this case, actually, x equals 0. Okay. So can we plug 0 here? Yes, because 2 times 0 plus 1 equals 0 plus 1 is still 1. So inside of log is still positive number. So y is 0 is x equals 0. So that means that 0, 0 is a point on this graph. There's actually an x-intercept and also happens to be a y-intercept.